welcome back everyone to the Hello World Guide. This is another episode of the OpenGL Tutorial Series, and in this video we are going to be taking a break actually from the rendering and pipeline stuff that we have been doing in the previous few videos. And in this video we are going to be focusing on another aspect of OpenGL and graphics programming in general, which often gets overlooked in beginner tutorials but is actually very important, and that is debugging. Now the debugging of graphics stuff is actually understandably quite different from traditional CPU side debugging, because of course that is occurring on the GPU and the model of execution of the GPU is quite different from that of a CPU. And we are going to, in this video we are going to look at mechanisms present in OpenGL for example logging any messages from the OpenGL implementation for any errors or warnings, as well as some other tools. In particular we are going to be looking at Renderdoc for understanding how we can use that to debug our program. And this is very important to get right, because sooner or later you are going to run into issues from your program, and when you just get a blank screen there is not much you can do about it, and instead of outputting random colors to the screen to figure out what is wrong, the better way is to use a tool like Renderdoc, as well as built-in API validation and debugging to figure out if you are doing something wrong. So to get started, we are going to go ahead and we are going to add the debugging code here. Right after we initialize our glue, before we create anything, we should set up our debugging. And in OpenGL there are actually various different ways you can debug, and the old method was to use this function called glgetError, and every time you did something that was not correct, it would actually give an error set, like an internal error variable, and you could use glgetError to get the last error. And this is, as you can see, quite a what you can say, a very fragile and not actually a very robust way. So in modern OpenGL, and this was first introduced as an extension in OpenGL, but in the version we are using, it's now a part of core, we have got actual debug output. So in order to use that, we can use the function GLEnable, and we can go ahead and this GLEnable function, by the way, is an important function in OpenGL. We can use it to enable or disable. There's also GLDisable. We can use these functions to enable or disable a variety of different capabilities on OpenGL, and the one that we want to enable now is GLDebug output, and this actually will allow us to essentially the OpenGL implementation will generate debug output on anything that we do wrong, and we can then log that to figure out if something is going wrong. It can also log additional informational messages, and we can actually insert our own messages into the debug stream. We'll maybe use those different tricks later, but for now we are going to just use the default. So we are going to enable the GLDebug output. Now there is a problem with just enabling this, which is that this GLDebug output can actually call our debugging callback. So we'll actually register a callback function which will be called whenever OpenGL wants to log a message, and since the OpenGL implementation or the drivers implementation that's running this can be multi-threaded, so it can be executing different parts of our code on different threads, and this will by default actually call the callback that we give it, the callback that we register from whatever thread it's currently executing where the message gets generated. So this means that our callback function needs to be thread safe to call, which means we'll need to do our own synchronization and everything to make sure that nothing goes wrong. Now that is a bit of work, and in order to actually prevent that, we can enable another capability, and that is GLDebug output synchronous. And what this will do is this will basically force the implementation to do its own synchronization, so that we don't actually have to worry about that, and it will essentially it will do the synchronization on its own, and we can assume that our the function that we register is being called only from one thread, and we don't actually need to make it thread safe. So after that, in order to actually register which function we want, we can use the GLDebug message callback function, and this function allows us to give it a callback as well as a user parameter. The callback is the function that we want to be called whenever OpenGL wants to log a message, while the user parameter is any arbitrary parameter that we can set here which we want to pass to this function. So in order to set this function, we are going to define a function called GLDebug in a second, which we will pass here, and for the user parameter we don't really care about that, we can pass null pointer. Now if I open this up actually, and we can open up the you can see we have got our GL debug message callback. Yeah, here is the basically the definition for GL debug proc. So this essentially is the function that we want to be using here. It is as you can see, it has a GL enum, source, and the type, ID, severity, length, and other parameters. We basically want to take in all of these parameters and essentially basically do whatever we want with them, which basically means logging. So we are going to go ahead and in here we are going to define a function here. So we are going to say void gl debug, and we are going to basically paste this here, and let's go ahead and actually copy this and take it down here, and we can go ahead and paste it here. Let's actually put this up here. Now as you can see here, the GL debug function, the callback takes a lot of parameters: the source where the message came from, the type, the ID of the message, severity, etc, etc. We don't really care about those, and we are going to only we only care about the message which we just want to print for now. So we are going to just go ahead and use fmt print and print our OpenGL debug message like that, quite simply. Now before we actually try to run this and see what happens, another thing we need to do is when we are creating our window, we need to give it another window hint, which is that glfw OpenGL debug context, and we need to set this to true so that the context is created with debugging functionality. Now if I go ahead and run make, for example, you can see that we get this, and it actually gives us an OpenGL debug message. Now this debug message is an informational message, it's not an error or a warning. It just gives us information about this buffer that we are creating, saying that it is bound to none, and the usage is GL static draw, and it will use video memory as the source for buffer operation, which means, well, it's just basically an informational message, and we don't really care about that. The only thing we care about is messages which are warnings or errors. Now in here there are basically two ways to do the filtering. One is to just take the severity parameter and use that to essentially, if for example the severity is a certain severity, we can print the message, otherwise we can ignore it. And it is also possible to set this up with GL debug message control here. So we can use GL debug message control, and this function can take different values, and we can tell it whether we want to enable or disable it. Now we only want to disable certain severities, and for that what we can do is we can first of all pass GL don't care for the values that we don't care about. For example, we don't care the type for the type or the source, or the we actually do care about the severity, and we can for example set the severity to GL severity GL debug severity high, and this is the error severity, and we can for the count, and this is the count of the certain IDs that we want to enable or disable. We don't really care about those, we are not doing any certain IDs, so we can ignore that, pass 0 and null pointer. And for the enable, whether we want to enable this or not, we can go ahead and say that we do want to enable these. Now what will happen is that if I run this, we will actually still get that message, which is because by default all are enabled. So what we'll first do is we'll set GL enable to false, and we'll use that to set GL severity to GL don't care, and this will set all messages to turn off, and then we'll turn the errors on, as well as the warnings with GL debug severity medium. So if I go ahead and run it now, you can see that we actually don't get that message. This is because we have obviously disabled any severity that's not medium or high. And we have, apart from medium or high, we have also got GL debug severity low, and I think we have also got a GL debug severity notification. Yeah, and this basically is the lowest severity, and I think that message that we got was actually a notification, so we can safely ignore that. And now we can actually test this by trying to do something wrong. For example, you can see here we are passing GL name buffer storage. So if I go ahead and pass 0 for the buffer, which is an invalid name, you can see that it actually gives a message saying that GL invalid operation generated because an invalid buffer name. Now of course it does not give a lot of information about where exactly that occurred, but there is not much we can do about that. That's just how OpenGL debug functionality is. It's not very awesome, but it does work to some extent, and it can give you an idea. Alright, so now we are going to look at the other type of graphics debugging that we are going to be doing in this tutorial, and that is using an actual graphics debugger. So here you can see we have got Renderdoc, and Renderdoc, if you do not know, it is an open source graphics debugger that works that is multi-platform, and it works with different APIs like OpenGL, Vulkan, as well as Direct3D. And here we are going to use it to debug our OpenGL program. So after you have installed it, you can install it quite easily from the website, or you could try to get some pre-built binaries, or you could build it from source. On Linux, on Windows, you can usually get pre-built binaries. And here we have got the Renderdoc interface opened up, and you can see here we have got the different tabs here, and I'm in the launch application tab, and this is where we are going to start. So the first thing we are going to have to put here is our executable path, which is the program that we want to run. You can optionally specify a working directory as well if your app loads some assets and it needs to have a specific directory as a working directory. And we have also got some command line arguments or environment variables that we can set. We don't really care about these right now. And now for capture options, these are options that we can set for certain things. And in here we can, for example, enable API validation, and we can have it reference all resources. For example, it will by default it will only consider those resources which are used in the particular frame that we are trying to capture and analyze. And if you check this, it will include all resources, and we've got some other options here. For now, you can just leave these at the default, and we can go ahead and try to actually run this. And this we can actually queue the capture so that it captures a specific frame range, but we don't actually want to do that. We can do it manually. So if I hit launch, you can see that the program starts here, and it's displaying an overlay here saying that it's capturing OpenGL, and it's giving the frame index as well as how much time it's taking and the FPS. And we can press F12 for print screen to capture a frame. So if I press F12, it will capture a frame. You can see it captured frame 904, and one capture has been saved. So if I close that, it will, since we have got only one capture, it will automatically open that capture. So here you can see that it starts off at the final output, at the final GLX swap buffer stage, and this actually renders the screen. And this is not called by us directly, this is called by GLFW in GLFW swap buffers. And apart from that, we have got in this event browser, let's start here because this is what displays everything that happens in our frame. So you can see this event browser essentially has a bunch of different actions or events, and these are the things that we actually did or happened in our program. So first of all is the capture start, which is when the capture started. And by the way, you can notice that some IDs are skipped here. That's because by default it has a filter which only displays actions that actually do something instead of other stuff as well. So if we remove that filter, you can see it also displays this context configuration. We don't really care about that. We can add that filter back again. So the first thing that we do, as you can see from the program as well, is the gl clear command, and you can see it tells us that it clears it with a yellow color. So if we open that up, you can see it is only clearing the color buffer bit, and it displays the color here as yellow 1101. And you can see, actually you can dynamically see the output of each stage. So when we do gl clear color, you can see that the outputs, which is the back buffer color, which is what we are drawing to, and you can see that becomes yellow. Now if you go under gl draw arrays, it of course draws a white triangle on top of it. So yeah, this is basically pretty much it for actually what we have in our program right now, but we can go a bit deeper into this gl draw arrays command, because this is the one that is actually drawing the triangle. So currently we are in the texture viewer, but if I go ahead and move on to our pipeline state, this is basically a state of the whole OpenGL pipeline. So the first stage is the vertex attributes, which are the actual things that we pass into our shader, and you can see that in here it actually gives us the vertex attribute formats as well as the vertex array object, and we can analyze the vertex array object here as well, and you can see what commands were used to initialize it and in the resource inspector. And it also gives us the buffer, and this is just the raw buffer, by the way. We can go ahead and view its contents, and it gives us the raw contents, but we can specify a format here to actually see contents in a human readable way. We'll do that in a second. So if I go here, you can see that in our vertex attribute formats, at index 0 we have got an enable format which is named a underscore pose or position, which is what we named it in the shader. And in the format or the generic value, we've got R32 G32 float, which essentially means it's vector 2 since 2 floats. And then we've got a buffer slot of 0 and a relative offset of 0 since it's the only attribute and it's at the beginning. Now I can click this go button here, and we can go back and go into the mesh viewers page. Now this actually shows us all of our data of the vertex input, our mesh. We can see that the VS input was this, it was essentially a uniform triangle, and the VS output was this because when we apply this to a normalized device coordinate state, it's not a uniform triangle anymore, because obviously we are assuming that the space is uniform, which it is not. So you can see that this we can analyze the input and the output. As well as that, we can also analyze how our are the numerical values of our data here. So we have got the vertex 0 and the index 0 as well. We are currently not using any special indices. We'll do that in the future as well. And then you can see we have got all of those values that we originally put in our vertex buffer. Now if I look at the vertex output stage, you can see the only thing we are outputting right now is the position. We are not outputting anything else, but you can see that the position is essentially the same as this, but with the 2 extra coordinates. So this is our mesh viewer. Now if I go back under pipeline stage, we have got the vertex shader here. You can see we are not accessing anything in the vertex shader. Currently it's pretty simple, but I can actually go ahead and view our vertex program here as well in main.glsl. There's also a disassembly here, but we don't really care about that. That's a different thing. So in main.glsl, you can see that this is basically the exact string that we passed into into our program, and it's basically taking that exact string here and putting it, displaying that. And if I go ahead and look at the next stage, you can see we are not using any of these tessellation stages or the geometry stages, geometry shader stage, but we have got our rasterizer, which is actually doing the rasterization. Of course, this does not have any programmable pipeline or programmable shaders, but of course this can display as a bunch of different rasterizer state. Now this is all of the state that OpenGL has, and you can analyze this here to see if something, for example, was wrong here, set wrongly here, which was causing something to not be rendered correctly. But we have in the future we'll of course analyze what each of these means as we learn more of OpenGL. Currently we can skip ahead to the fragment shader stage, and as with the vertex shader, you can go under view to actually see the shader here as well. And as you can see, this doesn't access anything special here, and we have got the frame buffer stage, which is the last one when the output actually gets transferred. And you can see that we actually transfer to our back buffer color. It's a texture 2D, of course, a two-dimensional texture, which is the screen that we are rendering to, and we essentially put different data here. And there's also the depth stencil buffer. We'll understand depth stencil buffers in the future, but currently we don't really care about that. The value written here doesn't matter. Apart from that, this is pretty much it for the pipeline state, and we have already looked at the mesh viewer. In the resource inspector, you can see all of the resources. You can sort them alphabetically or by creation type. So the first thing that was created, of course, was the context, and along with that, default VO is created by OpenGL. And then we have also got a back buffer FVO, which is the main thing that we are trying to, and this is the first buffer that we actually create, our own buffer, as well as the vertex array we create, the 2 shaders that we create, and the program that we create, as well as these are different things that we actually don't create. These are managed internally. So anyways, this is pretty much how you use Renderdoc, and of course currently a lot of this stuff is going to look overwhelming because we haven't actually gone deep into OpenGL, and this is displaying a lot of different things, for example in the rasterizer state that we have not yet looked at. But in the future, as we understand more and more of OpenGL, you'll learn that this is actually quite a useful tool, and we can use it to analyze a lot of different things, and it really does make debugging, graphics debugging, a lot easier. So anyways guys, this is going to be pretty much it for this video, and I'll see you in the next one, and make sure to like and subscribe as well, and share this video with other people, and bye.